All right, let's get started. My screen visible, right?
Yes, sir.
Yes, sir.
The contents for today will be echelon form. Let's call it echelon form. And then row reduction. All of these are related topics, which will eventually lead to Gaussian elimination. So what we saw last time, a very brief recap, was the first part of the last session was about how to compute determinants of a square matrix, and we saw properties basically. The computation of the determinant was covered in week one, and some ways to possibly reduce the computations and some properties we saw last time. And we saw that determinant not being zero is a special case in the context of solving the system of linear equations. If, in the sense that if you have a coefficient matrix which is a square and invertible matrix, meaning the determinant is non-zero, then it has a unique solution. And we saw two methods of computing it. One is just by multiplying by the inverse of the matrix. We saw how to compute the inverse of the matrix and multiply it with the constant vector to get the unique solution to the system of equations. And the other one was using Kramer's method. Now, in this session, we'll see how to do the more general approach for possibly non-invertible square matrices or more generally rectangular matrices. Is there a problem with the audio or?
There's no problem, sir. You're clearly audible.
It's perfect, sir.
Okay. All right. So let me just write that down. Recap is determinants and solving Ax equal to b when A is a square matrix with determinant of A not equal to 0. That we saw two things, which is one of it is Kramer's rule and then using the inverse, right? I hope everyone is comfortable with this part now.
Yes,
Are
sir.
there
Yes, sir.
any doubts from the last session, or should I go ahead?
Go ahead.
Sir, at last, sir, can you just explain the using the universe part at last, if possible, after session?
Sure. Okay. If you have Ax equal to b, the unique solution to that is x is equal to A inverse b. And how to compute the inverse we had discussed last time. If you want, we can take it up at the end again.
Yes, sir. Yes, sir. That will be nice for me, sir.
Okay. Okay.
Thank you, sir.
So right now, let's go to row echelon form. This is mostly just formalizing what you already know. So suppose you have, let us take an example of a system of equations that I'll not specify what the B is, but let's say you have an upper triangular matrix, a 3 cross 3 upper triangular matrix as the coefficient matrix. I don't know, put some random numbers here. So what would the corresponding system of equations be? It would be
Yeah, 2x minus y.
yeah
Minus y plus 6a.
plus 6x3 is b1, whatever that b1 is, and then you have
Yes, sir.
3x2 plus 5x3
plus 5x3 equal to b2.
And then you have 4x3 is
4x3
equal
equal
to
to
b3.
b3.
So such a system, of course, visibly is very easy to solve, correct? So here you will directly get from the third equation that x3 is equal to b3 by 4. And you will get x2 is some b2 minus 5x3 divided by 3. Put the x3 value from the previous thing, but we'll do the back substitution. And x1 is b1 minus 6x3 plus x2 divided by 2. So for this, you don't need to have any other method. Or let's go slightly more complicated, but in the same spirit. Let's say we have A is equal to, let's take a 3 by 4 matrix, for example. Say this, this. This is not exactly upper triangular, but this still has certain pattern, right? Which I will explain more clearly when I explain the general method. But suppose you have this as your coefficient matrix. Once again, we can decode this and write the system of equations as x1 plus 3x2 minus x3 plus x4.
Sir, I want to ask one thing, sir, from the previous example.
Yes,
Sir, how that 4, 3, and 2 is coming
which 432?
when the denominator for
So here
B3 is like,
4x3 is b3, correct?
okay, and the x2?
For x2 also, you have 3x2 will be equal to b2
Okay,
minus
from
5x3.
equations you are taking. Okay, sir,
Yeah,
got
yeah,
it,
yeah.
sir.
Just from this thing, I'm deducing. I'm trying to solve the equations. But
Okay,
in the
okay, sir,
case
got it.
of an upper triangular matrix, I'm just saying that there is not much to solve. Just use the one with the least number of variables and then just keep back substituting other things.
Okay, sir.
Yeah. In the next example, also we see something similar. So here you'll have x1 to x3. So b1 to b3. 3x
3x4, yeah,
is
equal to
b3.
b3.
Once again, you see that you have one value immediately by equation 3, which gives you this thing is b3 by 4, right? And the next one would be x2. Like if I substitute this in this, I'll get
Yes, sir.
this is from equation 3.
Score
Let
equal
me
to
write
B3 by 3,
this
sir.
is from equation 3. This is equation 2. This is equation 1. Sorry, b3 by 3. Sorry, yeah.
And sir, in the
x2.
first equation, it is x1 plus 3x2 minus x3 plus 4x4 equal to
Oh, right.
dot on f4. Yeah, yeah,
Okay. So from equation 2 and using 3, we'll get that. Well, I'm not going to explicitly write that, but I'll just mention that this is b2 minus 5x4. x4 in turn is b3 by 3, so you can substitute that and get the value. And the first equation, if you check, you'll see that x1 is equal to b1 minus 4x4 plus x3 minus 3x2 divided, there's nothing to divide. So this is already in a 1. So this is actually equal to this. This is fine. This is fine because you have some constants. B3 and B2, even though they are not determined, they are constants. They are not explicitly specified in this thing. They are constants. So this is fine. So when you're substituting back in x1, your x4 and x2 are okay. But what about x3? x3 can actually take any value, right?
Yes, sir.
And,
Yes.
and depending on the value of x3, you get x1. So there are like infinitely many solutions, one for each x3. So in that sense, x3 is an independent variable. All of this will be made even more clear when I explain to you reduced for reduction using row operations and all that. But here you see that you cannot completely determine a unique solution. There's definitely a dependence on x3, which can be any number. If we in particular take, let's say, to make it a slightly less confusing, if I take it to be, let's take this to be 3, so that I get nice numbers. And let's say 5, and let's say 1.
Sir, x1 is also dependent in this case.
These three are dependent. x3 is independent.
Sir,
So
Yes.
just wanted to ask, like, why is x1 dependent in this case?
sir, you have
I'll
written
explain that.
Okay, fine, understood. Got it.
so
Yeah, the other
you,
doubt, yes.
you have written x1 in terms of x3. Can I write x3 in terms of x1 last?
You can do that. You can do that. This is not a unique way to do it, but in the prescribed way, you'll see that this is how it comes out. Okay, so in this case, for b is equal to 351, all of this will be clear when I tell you the general method. Uh, right now, I'm just giving you examples to say that if I have, zeros over here in a certain pattern, like in this case, in the lowest equation, you have only one variable, so that you can determine, and over here you have just one more, and so on. So you can keep determining things once you have this sort of an arrangement. So you have maximum non-zero entries over here, and then you have lesser non-zero entries here, lesser non-zero entries. So you can start by determining this, and then substitute in this, and then substitute in this, and then substitute in this. This is what you all generally do while you're solving equations as well. You try to eliminate variables and try to get the value of one of the things, and then keep back substituting, right? So this is just reformulated in the matrix language, and let's see how. Uh, Before that, let's compute this for specific b is equal to 351. Here we'll just get it to be 5 minus x squared is 1, so this is 0. Here you will get it as oh wait.
Sir, x4
One
equal
five.
to 1 by 3, sir.
1 by 3, yes.
Okay. Yeah, it's correct, sir.
Yeah, I just wanted nice numbers, not fractions. So it is.
Hmm.
Yeah, this is okay. Now b1
Yes,
is
sir. Yes.
1 minus 1 minus 4
4x4.
plus
1.
x3 minus, see, this is just minus 3, right? Now the general solution to this system of equations will be of the form minus 3 plus x3, 0, x3, 1, correct? So the most general case is that when when the coefficient matrix is in reduced form, let's not say reduced, let's say echelon form. Reduced I'll talk about later. Echelon form, then it is easy to solve. Now, what is echelon form? I've not said what is echelon form. So this is the description of echelon form. The first non-zero entry in every row is 1. the first non-zero entry in every row, which is a 1 because of rule 1, occurs to the right of the non-zero entry in the previous row. And rows with only zeros are at the bottom. An example for an echelon form is something like 1 0 1 1 0 1 2 3 0 0 1 minus 1. Let's just take it this way. I'll explain each row. So the first non-zero entry in every row is 1. So you take R1. What is the first non-zero entry? That is 1. So in the second row, this is the first non-zero entry. That is also 1. In the third row, this is the first non-zero entry. This is also 1. So in every row, well, the row could be entirely zeros. That is okay. But if it is a non-zero row, then the first entry has to be 1. So this is actually not in echelon form. This matrix is not in echelon form. It is close to. You can after scaling, you can make it that way. So the first rule is that you look at each of the rows, and the first non-zero entry has to be a 1. The second rule says that the first non-zero entry in every row occurs to the right of the non-zero entry in the previous row. So you look at, so that rule vacuously does not holds for the first row. Now you look at the second row. You see, this is the first non-zero entry, correct? This has to occur to the right of the non-zero entry in the previous row. So what would not be acceptable is something like this. I'm just putting zeros just to finish it up easily. So here what is happening, the first non-zero entry in R2 in R2 is to the left of the first non-zero entry in R1. Correct? So this is R1, this is R2, row 1, row 2. This guy is to the left of this guy. That is not permitted. Right? Even things like this is not permitted. If they are on the same row, that is also not permitted. What is only accepted? So this is not in echelon form. Echelon form has to have it to the right. And this is not just for R2 and R1, it has to happen for R3 and R2 also. But that we can check, right? So if this is the first non-zero entry in R3, and that is to the right of this, it may well happen that there is something in between, like 1011, 0103, 0001. This is fine. It need not be one step to the right of it. It can be 2 steps to the right. But the only condition is that every first non-zero entry is 1, and they sort of form something close to an upper triangular matrix. Like an upper triangular matrix makes sense only in the context of square matrices, correct? But in this case, it just says that when you compare it to the previous row, this has to be to the right of it. And rows with only zeros are at the bottom. That is, you can just.
Sir, what if in the second matrix, the first non-zero entry, that is 1 in the R2, is in the third column?
So this one, it's like this is what you're asking?
Yeah, and the one below it is in to the right.
This is what you're asking?
Yeah, this is what I'm asking.
This is fine.
Okay.
if suppose, sir, in second matrix, R2 will be the R2, the last one column will be 1, like this.
You're saying this is 1, 1?
No, no, R1 will be the last column will be 0, and below that, this is 1.
This?
Yes, sir. And
This
this
is
one,
okay.
left side one is 0.
Left side, this is 0.
Yes, sir.
This is not okay.
This is not okay.
Sir,
Yeah,
Because
upper,
of that,
so this
R3 have a,
I couldn't hear you clearly. Could you repeat that?
because of, sir, R3 in R3 and column 3, the last
Aha.
1 and 1 is below.
Yes,
Both-
it is not to the right, right?
If it is the 0 last row, then it will be okay.
This is fine. Yeah.
Okay.
And sir, if it will be 2,
Sorry, the first entry has to
Last-
always be 1. As in the first non-zero entry has to be always 1.
third row, last element 2. Yes.
So
Yeah,
here
this-
the condition was
This is not satisfied in that case.
so we have
So
to
the
follow
pro-
this 3 condition, correct?
Yes, whenever these 3 conditions follow, then it is said to be in echelon form.
Okay, now those my doubt is, see the second row also we have the left side is the 1, correct? Sorry, right side
Yes.
is the 1. So that is a 2 condition record, and final third condition always 0 0 only bottom, correct?
Yes, so this is okay, but this is not because the leading entry of row 3
Okay.
is not to the right. It is not even okay if it is equal. Well, you can convert it using one step, which we will see. But as it is, by the word of the law, this is not okay.
sir, so
If
this,
the middle row
This is not
was
satisfied.
completely 0, then it is fine.
Yes, that is fine. That we have answered. 0 is okay. 2 or anything else is not okay.
No, I'm asking in the R2 if the last entry is 0 and the third
Okay.
row it is the last one is 1. Is it fine?
Is this satisfied? Is this a third condition satisfied?
Okay.
No, right?
No.
so this upper triangular matrix will only be in case of the square matrices, right?
Right.
Okay.
Sir, according to the third number, that means the zeros with all total 0 can be only at the bottom row.
Not only the bottom row, it should be below every non-zero row. You can have multiple also. You can have like 1 0 0 1 0 0 0 0. This is fine.
Okay, sir.
Are at the bottom, meaning there should not be any non-zero row below any 0. Okay.
Sir, in this example, like we can
Which one?
change the this one, like last one row.
M1, M2, M3. Which one?
We can change the position of row, no?
Change the position of which row?
Like row 2 and row 3.
No, I'm not talking about operations, row operations yet. I'm just seeing, given a matrix, is it in echelon form or not? That is all we are discussing.
Okay.
Sir, in M3,
Mhm.
you can see the third row, the last one is the one is coming, correct? The fourth column. Sorry, fourth column,
Yes.
third row.
Yes.
So that is a condition for this echelon form.
This satisfies echelon form. M1 and M2 are in echelon form. Sorry, M1 and M3 are in echelon form. M2 is not.
So actually, we have to follow only row 1, row 2 only, correct? That position of the 1, correct?
Every row has to satisfy these 3 things. As in, okay, the third rule is that only zeros
But
should be at the bottom.
my
That
doubt
after we have
is,
verified.
my
Yeah.
doubt is the M3 is the third row, last one is there, no? Fourth column.
Yes.
But but this is okay, that condition.
That is okay. No? So first of all, let's check with condition 1. Is the first non-zero entry in row 3 1? Yes. Is the first non-zero entry in row 3 to the right of the non-zero entry in the second row. The previous row in this case is the second row. It is to the right.
Okay. Okay, that's all I'm confused now. That's one is there, no? No, yeah.
Sir,
So it
Yes,
need not be
understand.
one step to the right. It can be two steps to the right also. That's fine.
Okay, thank you. Thank you. Now clear, sir. Thank you.
Yeah.
sir,
Yeah.
sir, for getting row echelon form, sir, can we do column switching?
I have not even discussed can you do row switching, right? Right now I'm just saying what is echelon form. I have not told you how to get there. We'll discuss that.
Okay, sir.
Sir, one question, like just I
Yeah.
think is correct or not. What is the objective behind this echelon form? What will we solve
So
using?
suppose, yeah, so the big picture is that in general your matrix can look anyway, but once you get it in this form, can you see that the equation is easier to solve?
Yes,
Let us
easy.
take for example this one. Again, let's say 0, 0, 0, 0. It's like Ax equal to 0. The homogeneous system of equations is what you're trying to solve.
Yep.
Here you will get by the let's write down that, right? X1 plus X3 plus X4 is equal to 0. X2 plus 3x4 is equal to 0. And X4 is equal to 0. Correct?
Yes, sir.
So because of the design of having the leading entries of one row to the right of the other, what you will have is that the lowest non-zero row,
Yeah.
it will have very few variables or very few ones, which will correspond to very few variables. So in this case, that is x4 is equal to 0. And as soon as I have x4 is equal to 0, I'll get x2 is equal to 0.
0, yes, sir.
And as soon as I have that, I'll have x1 plus x3 is equal to 0.
Yes, sir.
So here it is not completely determined. You have x1 is equal to minus x3.
Minus
More
X.
generally, whatever these leading ones are there, you can write it always in terms of the other ones. I'll discuss this also more clearly later.
Okay,
but
sir.
this is for M3, correct? So your solution in this case, x2 and x4 are 0, and you have minus x3, x. So, or I'll just take it as minus t. Okay, and t is in R. Any real number. Any number of this sort is a solution. Like this set is the whole solution set for the given system of equations, correct?
Yes, sir.
Yeah. Now here things are much simplified because of it being in echelon form. Similarly, if we write it for M1, if you check.
Sir, can we say that like this has infinite solutions?
Yes, this has infinite solutions. No, there are infinitely many real numbers.
Okay, okay.
Yeah. So any number of this form, if you check that irrespective of what the value of t is, this minus t 0, t 0, this will be a solution. You can check that by plugging it into the equation. So t can be infinitely many values means that, of course, your system of equations has infinitely many solutions. So let's now write down.
How do you the minus t and 0 that elements?
So this is x1 is equal to minus x3, correct?
Yes.
Whatever x3 is, x1 has to be negative of that. And x4 and x, you have this. X4 is forced to be 0, x2 is forced to be 0. And then x1 is forced to be minus x3.
Okay.
So this is 0, this is 0. And whatever this is the negative of that.
Okay. Okay, sir. Okay, thank you.
So you could write it as t minus t0 also if you want, but it is the same thing. It spans, the solution space is the same. There is a reason why I'm writing this. We'll see that later. x1 plus x3 plus x4. This is, let's come back to M1. This is equal to 0. For non-homogeneous system of equations, it's similar. The procedure is similar. 2x2 plus, sorry, x3. If I make mistakes, please point it out. Right? This is 0, and you have x3 minus x4 is equal to 0. So this is the system of equations for M1, which is also an echelon form, by the way. Now, the first equation or the last equation here gives me x3 is equal to x4. The second one gives me x2 is equal to minus 2x3 minus 3x4. And the first one gives me x1 is equal to minus x3 minus x4. Now, as soon as I have x3 is equal to x4, I can substitute that over here and get minus 5x4. Correct? Because x3 is x4. So you'll get minus 2x4 minus 3x4, which is minus 5x4. And minus x3 minus x4 will become just minus 2x4. Is this clear?
Yes, sir. Yes, sir.
Yes, sir.
So what is the general solution to this system of equations? Let's say in terms of some r.
T minus 2t
minus 2t
Minus
minus 5t
5t
dt.
and t.
minus 5t tt.
Correct?
Yes, sir.
So each of x1, x2, and x3 have been written in terms of x4. And x4 is the independent variable. So x4 can take any value. And x1 and x1, x2, and x3 can be expressed in terms of the independent variables. So those are dependent. So x1, x2, and x3 are dependent variables. And x4 is an independent variable. Just understand this in spirit right now. The formal definition of an independent variable I'll give later. So now you have reasonable clarity on what echelon form is, right?
Sir, why aren't we assuming here that x4 is independent to x3 and like?
Well,
why
I'll get to that.
Okay.
I'll get to that.
Okay.
Yeah. You can do that as well. In this case, if this is one way of doing, this is the best way to do it in
Yes, we can also
an
say
algorithm.
x4 is equal to x3.
Yes, x4 is equal to x3, you can do it and then back substitute using x3 as well. But there is a reason why I'm using x4, which I'll highlight later. But right now, echelon form is okay, right? What is like how to check if something is in echelon form?
Excuse me, sir.
Yeah.
Sir, I didn't get the concept of dependent and independent variable.
Yeah, that will come later. I'll take it up later. For now, you just see that x1, x2, x3 can all be written in terms of x4, right?
Yes,
so
sir.
x1, x2, x3 are dependent on x4 in some sense.
Okay, sir.
More generally, if you have a leading 1 in some column, so look at this. This corresponds to x1. This corresponds to x2. This I'm talking about M3 over here. This column corresponds to x3, and this column corresponds to x4. Correct? Here,
Yes,
the
sir.
leading
Yes, sir.
ones occur corresponding to the variables x1, x2, and x4. Right? If you look at these leading non-zero entries, in which columns do they occur? In the circled columns, no?
1, 2, 4.
Yeah, 1, 2, 4. Consequently, here you see that 1, 2, 4 are dependent variables and x3 is the independent variable. This is the formal definition that wherever you have, for whichever column there is a leading 1 entry, that column corresponds to a dependent variable.
Sir, had there been a like in a 1 in row 3, say for example, so in that case x3 would have been a dependent variable, right?
Yes, so that you can see over here, no? So for M1, if I circle out the
Right.
leading row once, you will have x1, x2, x3 as the dependent variables, and x4 is the independent variable.
Okay.
And that is what we see over here. You can write x3 in terms of, x3, x2, x1 in terms of x4. So yeah, for now, you just take the following as a definition, that if there is a leading one in any column, if there is a leading one of any row, then that row corresponds to a dependent variable. And if there is no leading one entry in a particular column, then that row corresponds to a independent variable. If there is a one, it is dependent. If there is no one, it is independent. So this one doesn't count. It has to be a leading one. Is that fine?
Yes, sir.
Yes, sir.
Yes, sir.
So let me write it down. If a column contains leading entry, leading non-zero entry. Let me just write it down. Leading means first. Okay, that is non-zero entry of some row. Then the column corresponds to independent. It contains a one, then it will be a independent. So how to determine whether something is a dependent variable or an independent variable? You look at its corresponding column. So for example, let's remove this. Let's remove the circles also. Now I want to check if x2, for example, is for M3, I want to check if x2 is dependent or independent. For x2, I look at second column. In this column, is there any leading entry of any row?
So for column 2, row 2.
Row 2.
Yeah, the leading non-zero entry of row 2 is in column 2. So x2
Yes.
is dependent. Let's take a look at x4. For that, you have to look at column 4. And does it contain the leading non-zero entry of any row?
So row 3.
Yes.
Yeah, yes, that one was row 3. So that is also dependent. Now look at x3 to determine whether or not x3 is dependent or independent variable. Does it contain the non-zero leading entry of any row?
No,
Sir,
sir.
it is
No, sir.
Row 1.
slightly independent.
Yeah, so this is dependent, this is dependent, and you can check this also. This is also dependent, but this is independent. All right.
Excuse me, sir.
Yeah.
Could you please repeat it once?
Yes, sir.
Okay.
Sir,
Just
but
one
any
moment.
variable is independent with respect to other variable, like that x3 is independent to x4, and vice versa is also
X3 is
true.
independent. That's all. It's not independent with respect to anything.
Means x3 is equals to x4, so we can also say that x4 is equals to x3.
In this case, yes, but in the general case, it might not be.
Okay,
In the
sir.
general case, x3 might be equal to just some. You can have any value for x3, and x4 will probably dependent on. So you follow this algorithm, right? You circle all the.
Okay, sir. That is a particular case. That.
In this case, okay, I'll give you maybe towards the end an example where such a thing fails. This is not that easy to grasp. I get it. This dependent and independent thing is not very. Uh, when you write x4 is equal to x3, why do you call this as dependent and this as independent? Is not very obvious at the start. But for now, you take this as an algorithm. I'll probably give an example at the end of the session where it should make it more clear. So, but the
Okay.
algorithm is as follows. You look at the matrix, determine whether it is in echelon form. Now, if it is in echelon form, then you circle all the leading entries of the rows. Leading entries meaning the first non-zero entry. Okay, so the first non-zero entry of row 1 is 1, and that is what I've just done, right? There is no non-zero entry in row 4, so there is nothing to do over there. Now you look at the leading entries. They are in columns 1, 2, and 4, correct? This is column 1, column 2, column 3, column 4.
Yes.
Yes.
So 1, 2, and 4. Variables corresponding to those columns are x1, x2, and x4. These are dependent variables. That's what is written over here. If a column contains a leading non-zero entry of some row, then the column corresponds to a dependent variable. Whatever is not dependent is independent. So you circle or you mark the leading non-zero entries in each row, and those columns are dependent, the rest are independent. Is that okay?
So,
Yes,
so
sir.
In case,
am I audible, sir?
Yeah, please go ahead.
So, I just have a question. Like, here we know that x2 and x4 has a specific solution that is 0, but still we
Right.
are calling it a dependent variable. So it can be
Yes. So
it can happen, right? Even if we have solution, we can call the particular variable dependent variable.
even if it has, yes. So in some sense, it is dependent in the following. So what is the general case is that an independent variable, suppose your x2, this is not in reference to m1, m2, or m3. I'm just saying that in general, you may get something like, if suppose x2 is a dependent variable and say x3, x4, x5 are independent variables, you will get this as ax3 plus bx4 plus cx5. Okay, so the dependent variable is dependent on the independent variables. And these ABC could be 0 as well. So in that case, you do get a particular solution. So technically, this can be written as 0t, 0t.
Got it. Got it.
When you have only one independent variable, everything will be written as AT, BT, CT, BT. And T is a parameter, or T is a real number that can vary. Well, one of them will be an independent variable, so you will have something as T, and the others will be AT, BT, CT.
Okay, thank you.
You see that over here also. You see that over here also. You see that this even in this case, they have a -2t, -5t, t, t. So this is not an isolated occurrence. This is what happens in general. But to understand why it happens in general, you'll need a little bit more theory, which will come in the next week or the week after. But for now, you just take this as a rule that columns containing leading non-zero entries of rows are dependent, and the rest is the other one is independent. And the others are independent. And the dependents can always be written in terms of the independent. So you do see that the dependents have this 1 attached to them, right? So you will have, whenever you have a 1 followed by something, you will have x1 is equal to all those other things. Well, that's not a very good way to explain it. Later I'll give you another example, and there it will be clear. But for now, you just take this as a memorizing algorithm, which will be supported with an example. That dependent variables are ones which correspond to the columns which contain leading non-zero entries of rows, and the others are independent. Okay.
So x1 is an independent variable.
In both of these cases, x1 is a dependent variable. For example, in M3, x1, x2, and x4 are dependent, and x1, x2, x4 are dependent. X3 is independent. In this case, x1, x2, x3 are dependent and x4 is independent. Okay.
Okay, sir.
Next is reduced row echelon form. In echelon form, so reduced row echelon form is one extra condition to row echelon form. So this is row echelon form, correct? Now we have these special ones, no? The ones that have been circled. You see the columns that they are a part of, they contain other numbers as well. But if that is not the case, then we get what is known as reduced row echelon form. If the matrix is in row echelon form and columns containing leading non-zero entries contain have zeros elsewhere. Right? Then it is in reduced row echelon form, or RREF is what the abbreviation is. So once again, in words it might be a little difficult to grasp. So let's write out a matrix. If I have, say, 1, 0, 2, 0, 0, 1, 3, 0, 0, 0, 0, 1. Now this is in row echelon form or no? First of all, REF, is it correct? Is it in REF, yes or no?
Yes, sir.
Yes, sir,
Yes.
it is.
Because
Yes.
here you have a 1, here you have a 1 which is to the right, here you have another 1 which is also to the right. So REF is okay. But what about reduced REF, that is RREF? What is
Yes, sir.
RREF? You have to look
Reduced
at
row
the
echelon.
columns. You look at these, what are the columns which contain the leading row entries over here? It is C1, C2, and C4. C1, C2, and C4 contain the leading row entries. The condition over here says that it should have only that non-zero entry. Everything else has to be 0. So you check over here, there's only 1, 1, and everything else is 0. Here also there's only 1, 1, and everything else is 0. Here also there's only 1, 1, and everything else is 0. Here you have a 2, 3. You don't care about that. You only care about the columns which contain the leading ones, or in other words, the columns which correspond to the dependent variables. You look at that, and that has to always contain only that one, and everything else has to be 0. In comparison, if you look at M1 and M3, we know that they are in REF, but are they in RREF?
No, sir.
Either of them?
Yes, sir.
Which one is?
Sir, M2 is in RREF, right?
No, M2 is not even in REF.
No, the REF, sorry, yeah, because one is in the top, yeah.
Yeah.
M1 is in RREF.
No.
M1 is also not in RREF, no?
Oh,
Because,
yeah,
yeah.
yeah, no.
No one.
Mhm.
No one.
None is in RREF.
Mhm.
M1, M2, M3, neither of them are in RREF. M2 is not even in
Yes.
REF, but this is in RREF.
Yes, sir, it is.
So can you repeat this concept REF and
Which one do you want? REF also you want again?
yeah, one sir.
Okay, I'll quickly go through it, okay, because we have to cover the rest of the topics as well.
Yeah.
So you will have to look at each row. First of all, so in the first row, you look at, let's not take an example. Let's just describe the method first. In each row, the first non-zero entry has to be a 1. That is the first rule. The second rule is that in every row, the first non-zero entry, which will be 1 because of the first rule, has to come to the right of the one in the first entry in the previous row. So take for example M1. In R1, R2 and R3, in all three rows, you see that the first entry is the circled one, the one that has been circled in the note. Correct? Now
Yes, sir.
the one in R2, the first one in R2, the leading one in R2 is to the right of the leading one in R1.
Yep.
Correct? And the leading one in R3 is to the right of the leading one in R2.
Yes, sir.
So that second condition is also satisfied. The third condition is that just we need zeros, like the zero rows. In M1 there is no zero row. If there is any zero row, that has to be below every non-zero.
Yes.
Okay. So can you tell me why M2 is not in REF?
Sir, because sir M1,
Wait.
RO.
Let her answer.
Yeah, because first row leading coefficient is not 1, it's 0.
The leading non-zero entry has to be 1. That is the condition. The first non-zero entry has to be 1. That is satisfied. No?
Oh, second row, sir. Leading entry is not right to the first row.
Yes. So that is why this is not in RB. Is
Yeah.
that fine?
Yeah, yes.
So two things you have to check. Well, the third thing is just ordering of the rows. But the two things that you have to check is the first non-zero entry is always a 1. And that first non-zero entry, if you look at the previous row, it has to be to the right. Not even equal is okay. It has to be strictly to the right. It can be multiple steps to the right, but it has to be to the right.
Yes, I got it.
Okay. And for RREF, what you want is, in addition to those two rules, you look at these rows, look at these columns containing the leading ones. They have to have nothing other than that particular one. Nothing meaning the other entries have to be 0. In this case, you look at this column. This column is a column which contains a leading 1, correct? So if you look at this column, it has a leading 1 which has been circled. But there are other entries in that column which are 1 and 2. It is 1, 2, 1. That is not allowed. It has to be 1, 0, 0, 0, 1, 0 kind of a thing. In this case, in M3, you see, for this column, C1, you have 1, 0, 0, 0. For C2, you have 0, 1, 0, 0. This is all fine. For C3, you have 1, 0, 0, 0, but that is not a dependent row, or that is not a row which contains any leading one. So we don't care about that really. But then we do care about column 4, which contains a leading 1. But it has other entries in that column. There are non-zero entries in that column. There is a 1, 3, 1, 0, which is not acceptable.
So
this is
in
not in
M3,
RREF.
So in
sir, in M3 for the column 4, the first two element 1 and 3, if it is 0, then M3 can be RREF, correct?
Yes, yes.
Okay, sir, thank you.
And in the third column, it doesn't matter if another entries are existing, right?
Yes, yes. So that is the example over here. You know, so here you have a 2, 3 in the C3, which I don't mind.
Okay, fine.
Wherever there is a leading 1, these are the special columns. They correspond to dependent variables. They contain the leading ones. And if you want RREF, then you want that they are the only non-zero entries in those columns.
Sir,
Yes.
sir, I'll tell you one matrix. Please write it on black, means board, and tell me the answer
Yes.
whether it is in REF or not. In row 1, 0, minus 1.
What is the order of the matrix?
Sir, in row 1, 1, 0, minus 1.
No, is it 2 by 2 or 3 by 3? 3 by 3, I think. Sir. Yeah.
Sir, it is 2 by 3.
2 by 3. Okay.
Or in second row, 0, 1, 1. Yes, sir.
Is this in RREF or REF?
Yes, sir.
RREF.
REF,
What is
sir.
the
REF.
RREF.
Yeah, it's
RREF.
not.
It's RREF.
REF.
REF?
RREF.
Not
RREF.
REF. Everyone agrees
Yes.
that it is in REF.
Yes. Yes, sir.
Yes, sir.
Yes.
Yeah. What
Yes,
about
sir.
Yes.
RREF? What is the opinion?
Sir,
Yes,
it's
sir.
So
RREF.
it is
Two
not
independent.
RREF.
It's
It is
not
RREF.
REF.
It's
It's
REF.
RREF.
It's
RREF, sir.
Sir, it's
So what are
RREF.
the columns corresponding to the dependent variables?
REF.
C1, C2.
R1, C1 and C2.
So C1, C2 are the columns that we care about, correct?
Yes, sir.
Yes, sir.
And they don't contain any other non-zero entries.
Yes, sir.
So it is in RREF, correct?
Okay.
Independent.
Sir, REF and RREF difference then?
So if this was, let's say, 2, then this would not be RREF.
It is not REF also.
Because only one C1 is getting dependent. That's why.
No. The column containing the dependent variables, all the columns containing the dependent variables should have only one non-zero entry,
Which is one, right?
which should be
That is for
1.
REF.
No. For REF, you have these three rules.
Okay.
Correct. So the first non-zero entry has to be 1, and the first non-zero entry of each row has to be to the right of the non-zero entry of the
Yeah.
previous row. Now
Yes,
you look
yes.
at the columns corresponding to the leading entries, and those columns should not contain anything else other than that particular one. So you see over here,
Sir,
there is
in C3 then, sir, there is 2 entry.
there are 2 entries, but C3 is not a column which contains
Dependent variable.
Leading entry.
C3 does not correspond to a dependent variable, or C3 is not a column which contains the leading
Lead.
entry of any row.
Okay, sir, got it.
So you mark those leading entries,
Sir,
and you care about
how
only
we
those
come to
columns.
know that C1?
Understood, sir.
Yeah.
So how we come to know that C1 and C2 are dependent?
You mark the leading entries, right? So you look at row 1. Row 1, the first entry is this. Row 2, the first entry is this. Or here it is probably more clear in the first example. If you look at row 1, row 2, row 3, mark the first non-zero entry in each row. Okay, then you look at the columns corresponding to that. That is C1, C2, and C4. In the second example, you have again the circled ones as the leading entries, and those correspond to column 1 and column 2. Let's take another example. 0, 0, 0, 1, 0, 0, 1, 0, 0. This is not a good example, but okay. Let's if this is REF or RREF.
Sir, both.
RREF.
REF.
Both, right? So how do you go about doing it? Look at row 1, mark the thing. Look at row 2, mark the thing. There's nothing in row 3. So we have to consider the columns C2 and C3 and see if there are any other entries, any other non-zero entries in those columns. It turns out there isn't. So
It's both
this is in
REF.
RREF. So RREF means REF also. So I can just say this is in RREF.
So, sir, here C2 and C3 are dependent, right?
Correct.
The
Yes.
third.
Yeah.
And C1 is independent. Huh?
Yes.
Okay.
So if you try to write the solution to this, what will it be? It will be x2 is equal to, say, b1, x3 is equal to b2, and there's no condition on x1. Right? x1 is independent.
Okay. Okay, sir. Okay.
But yeah, so to actually see the dependence, you would want to write something like t b1 plus 0t, b2 plus 0t. All of this right now it might not make much sense to you, but when you talk about affine subspaces and all that, you'll see why this is formulated this way. But for now, just know that this is how it is. This is dependent. So RREF. So RREF is even more easy to solve than REF. If you have a matrix, coefficient matrix in RREF, just
Will RREF or REF will be in the form of a square matrix?
no, not necessarily. Here we have seen square matrices, non-square matrices, everything in REF, RREF, not REF, not RREF, even over here. This is, well, I can give you a square matrix which is not REF also. There is not, it has nothing to do with the size of the matrix. So does any of the rule feel like it appeals to some property which has to, which is dependent on the order of the matrix? No, correct?
So
Is there any
can I
dependence
simply
of the rules
So can
of
we
the order
explain
of the
that?
matrix?
Sir, can I simply say that the column which is containing the leading entry have only the entry, non-zero entry, right? Then it is
Yes.
RREF.
Yes. If you look at the leading entry of a row, consider its corresponding column, then there should not be any other
Yes, sir.
entries in other than that itself.
Okay, perfect. Sir, here M1 is RREF or REF, sir?
It is REF because the column 3, which is corresponding to the leading entry of row 3, has
Yes,
1
sir.
and 2 above it.
Okay, okay, okay. So it means leading entries column should be only non-zero entry in the column.
Yes.
Okay, sir. Okay, yeah, it's clear, sir.
Are all the doubts clear now?
Can you explain that 1 and 2 is quite confusion now? REF or RREF?
Which one? Which ones? These ones?
Yes, yes. REF and WREF.
So REF is okay. Is it okay that these are all REF?
And this one, reduced row incline forms?
No, no. Row echelon form is it fine?
Is fine, sir.
Yeah.
The leading
So
entry is.
when you have row echelon form, you will have that every column, every non-zero column has a leading entry as 1, correct?
Okay, sir.
That is a condition for row echelon form itself. You look at each of those leading entries and look at the corresponding columns. For example, let me remove the circles in this first example. The first leading entry is this. Look at its column. It has only zeros elsewhere.
Yes, sir.
Look at the second leading entry. Look at its corresponding column. It has zeros elsewhere.
Okay.
Right? Look at the third row. Look at its leading entry, which is the last entry. Look at the corresponding column. It has zeros elsewhere. This and this are zeros. So this is in RREF. So RREF requires that the column containing the leading non-zero entry of every row
There are also dependence,
has to
correct?
yeah, the columns corresponding to the dependent variables should have only one non-zero entry, which is the one by definition.
Okay, sir. I'm very clear. Thank you. Thank you so much.
Yeah. So
Sorry to
working
interrupt.
with examples and working with non-examples, both you have
So
to see.
what is the
This
what
is
is the minimum
just one moment. Just one moment.
minimum?
Let me finish this. Yeah. So take for example this leading entry of row 3 in example M1. In that corresponds to column 3, but in column 3 there are other entries 1, 2. It's not a 0, 0, 1. It's a 1, 2, 1. So this is not in RREF. Okay. Okay, yeah. What was the next step?
Yes, sir.
Yeah, sir. Sorry.
Sir, that means identity matrix by default will be RREF or REF.
Yes, yes. Identity matrix is in RREF.
Okay.
That is the ideal situation, right? Because if you have an identity matrix as the coefficient matrix,
Yeah.
then you already have the solution. No? You'll have x3 is equal to b3, x2 is equal to b2, and x1 is equal to b1.
But lower triangular or upper triangular may be or may not be if diagonal will be 1.
If diagonal is 1, then if it is upper triangular, then it will be REF, but unless it is identity, it will not be RREF.
Sir, shall I ask my question now, sir? I was holding
Yes,
on this
yes,
one.
yes, yes.
So, the number of what is the minimum number of column that has to satisfy here, sir? So, for example, right, if there is only one column that satisfies, say, 1, 0, and the rest all column has non entry 0 or like
This is also
yeah,
fine.
yeah,
This is in RREF. So all you have to do is you look at how many dependent variables there are. In other words, you see how many rows have non-zero leading entries, which will be just how many non-zero rows are there. And that many checks you have to do.
Okay,
In this
even
case,
that,
you have to
even
do
if it is
just one check.
Okay, even it is one column also, then it is fine. Then we can term it as
Yes.
REF.
Yes, this is in RREF.
If matrix contains only one element, one row, one column, means 1:1, single one.
Yeah, that's an identity matrix, right?
Okay. Then we
Sir,
cannot, this concept is not connected
Sir,
with RREF.
can we interpret it
But
in
sir,
way
This
something?
is trivially it is in RREF.
But
Sir,
sir, just want to ask, like, say for example, in the first row, like you just constructed a matrix right now. Yeah, the previous one.
Yeah. Okay.
In this one, like, both rows, second row and third row is zero row. They are zero rows basically.
Yes.
So, would they still be an RREF, or because
This is in RREF.
because only the last row needs to be a zero, right? Something like that.
No, 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 no. You can have any number of zero rows. All of them have to be below the non-zero rows. That's all
Below
REF.
okay, below.
Yeah,
Understood.
and at the bottom, meaning, so it is not just row, it is rows. Rows possibly many.
Rows.
It only is zeros.
Got
R
it.
probably it's better to write it as R below non-zero. Let's even say all rows with only zeros are below non-zero.
sorry. Sir,
Yeah.
can we interpret it here something like if our metric, my metric is RREF, then can I say
Yeah.
something for infinite solution, no solution, or unique solution? It would be unique solution, sir.
Not necessarily. So you take this for example, you will have
Mm-hmm.
x1 minus x3 is equal to b1 and x2 plus x3 is equal to b2.
Yes, sir.
And so this is x1 is equal to b1 plus x3 and x2 is equal to b2 plus b2 minus x3. Now x3 is independent variable that you can see from here also. C1, C2 are dependent and C3 is independent. Whenever you have an RREF form, the advantage is that you can take dependent variables to the other side and all the dependent variables will be on one side and you can write always an independent variable in terms of the dependent variables.
Sir,
Yes,
the
sir.
So
last
x3,
example you. Sorry, sir.
just
Yeah,
one
sorry,
moment,
sir.
let me complete this. So x3 can vary. x3 is independent. You can take any value for x3. Let us call it some t. Okay. And then
Yes, sir.
you have b1 plus t, b2 minus t, and t. This is your solution space. And as you vary, you will get different solutions. Now, here you can say that like if there is a column corresponding to an independent variable, then you'll have infinitely many solutions, provided you have solutions.
Sir,
It may
what are
so
the
happen.
uses of
So is your
Sir,
doubt
here it
clear?
means like C3 is making not clear for solution number of solution. But if
No, no, no.
C3 is not available here, if C1 and C2 is only, then we have unique solution.
So for a square matrix,
Yes, sir.
when you do R, what is an RREF for a square matrix? Let's take 3 cross 3. So it could be like 1, 1, 0. Everything else is 0.
Yes, sir.
Or something could be over here also. But you will have something like this or 1, 1, 0, the identity matrix. Or so it will be an upper triangular matrix, correct?
Yes, sir.
Because if you have 1 over here, then you can't have ones over here.
Sir, highest possible would be an identity matrix of 3 cross 3, right?
For 3 cross 3, identity would be uh, an invertible matrix in general. If you reduce it, it becomes an identity matrix. If you reduce it to row echelon form, it becomes an identity matrix.
Yes, sir. I was telling for RREF, for having the highest probability, the highest like number of ones which we could calculate. So it
Yeah,
should be
yeah, that is
identity.
identity matrix. Yeah,
Yes.
Sir, what is the use of a row echelon form?
that we'll see next.
Okay, sir.
Sir, in the
So,
above
but you do
example,
see that if you somehow get your system of equations to the coefficient matrix, if it is in the row echelon form or reduced row echelon form, you can readily solve it. That you can see, correct?
Yes, sir.
Yeah, but now next step is how to get it to row echelon form or reduced row echelon form.
sir, in the last example you mentioned that right 1 0 0 0 0 0 0 and all right. If the second, third, and fourth column has say for example 1 2 3 4 5 6 and 7 8 9, then it is REF, right?
No,
In
it's
that case,
not. So you're saying 1, 2, 3, something like this?
yeah, yes.
No, because your leading entry is not 1. This is not even REF. This leading entry is not 1.
Okay.
This leading entry is not to the right of this leading entry.
Okay. Okay, sir. Instead of 2, if I have 1 and 0 and 1 and 0, yeah, 1. So this one I can say that first row there is a leading, second row it is, the third also it has. So we can say as REF. Right?
This is REF, but not RR.
Okay. Yeah, yes. Okay, sir. Thank you, sir. Thank you. Got it.
Is everyone fine now?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Let's move ahead. So what we have dealt with is two specific forms for a matrix, row echelon form and reduced row echelon form. Now, if you have these matrices, the matrix to be in reduced row echelon form or row echelon form, you see that it is very easy to solve the system of equations. But your general matrix of coefficients will not be in that form. So next, the question to ask is how to change any coefficient matrix to row echelon or reduced. So let me just write this. And this, the answer is row operation. So the first row operation is multiply any row by a non-zero real number. Second one is add multiples of one row to another. Once again, I'll write all of these things and then I'll explain with an example, which is how it can be understood best in my opinion. What else is there? Swap rows is fine.
So are we going to get this PDF, sir?
Yes, as usual,
Okay.
you'll get the PDF in the dedicated folder,
Okay.
right? Yeah, these are the three. So interchange two rows, scalar multiplication, and adding multiples of one row to another. So let's start with an example again. Let's start with slightly simpler example, slightly simpler meaning smaller order, 2 cross 3. Let's start with a 2 cross 3 matrix. 1, 2, 3, minus 1, 6, 7, something like this. I don't want a 1, 2, 3. Let's do a 2, 2, 3. So is this in REF or RREF?
It is not in both.
It's not a RR.
Both are not satisfied, sir.
Yes. What is the obstruction that you see for this being in REF?
So firstly, there is not any one.
Yeah.
Yes,
So
sir.
the first check
Leading
is that
coefficient.
in the first row, the first entry is not equal to 1. So let's go, if you are going just by these rules, no, let me call these rule 1, rule 2, rule 3. I'll not go back to this position again and again. Rule 1 is that every non-zero entry has to be 1. Rule 2 is that every first non-zero entry has to be to the right, and all zeros should be below all non-zeros. So those are rule 1, rule 2, rule 3. Now, can I do row operations to bring this to REF or RREF? Let's see. So what are the permitted operations? You can multiply any row by a non-zero real number. So can I multiply row 1? So the first obstruction that you guys observed was that row 1 does not have 1 as the leading entry, correct? So is there any
Yes.
scalar multiple I can multiply the row 1 with to make that okay?
I think 1 by 2 R1.
1/2.
Yeah,
Yes,
let's
sir.
write
1 by
that
2.
as half into R1.
Yeah.
So what will I get?
1, 3 by 2.
And this is unchanged, correct? So our first obstruction is removed, that the first row now has 1 as its leading entry. So is it in REF now?
No, sir.
No, sir.
Not yet.
No, sir.
Not yet.
Not yet, correct? So what is the next obstruction that you can see? It's like you have to work with both rule 1 and rule 2 over here.
We need a zero
think
entry
that-
below the first non-zero
Instead of
entry.
-1, it has to be 0.
It has to be 0.
Rule 1 says that, rule 1 says that row 2 also has to have 1 as the leading entry. So if I multiply row 2 by -1, the leading entry will be 1, but that will not be to the right of the leading entry of row 1, correct? So I want the 1 in this position, and I want a 0 in this position. So how will I get a 0 in that position?
First, we can add.
Sir, add
First
row
we
1
have
and
to
row
add
2.
So row 2
Plus
becomes row 2 plus row. So technically, here also I have to write R1 becomes half R1. Well, this is R1 new is half R1 old. I'm not going to write everything explicitly. I hope you follow what it is. So if I add row 1 to row 2, I'll get a 0, a 7, and whatever 17 by 2, something
Yeah.
like that.
Yes.
Is that correct?
Right. Right.
Yes, sir, correct.
Yeah. Okay. We'll continue over here. But is it in REF now?
Not yet.
No, sir.
Not yet.
No.
Right. So what do we do next?
We divide
We
by
can
Now we
divide.
have to
We
convert
have
it
to
to
divide
value.
multiply
on
1 upon
1 by 2.
7 to
R2.
R2.
R2 becomes R2 divided by 7.
Yes.
We have a 1, 1, 3 by 2, 0, 1, 17 by 14, something like this. Okay. Now are we in REF?
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
So REF is attained over here. But this is this in RREF?
No, sir.
Yeah.
No, sir, it's not.
No, sir.
Can we make it into REF, RREF?
Yeah, we
Yes,
can.
sir.
Sir,
R1
subtract
equal to
Subtract
R1.
second row from
Subtract
first
second
row.
row from R1.
Sir, but that one will get affected with that.
What do you want to do? Tell me in terms of how we are writing over here.
First, we can do
R1 minus R2.
R2 R1 minus R2.
R1 equal to
R,
R1 minus
R1
R2.
equal to R1 minus
R1
R2.
changes to R1 minus R2, correct? So
Yes,
what
sir.
will be the resultant matrix?
1,
1
0.
minus 1, 0.
Yeah, you're telling in terms of columns, right? Okay.
0, 1.
0, 1,
70.
4 by 14 and 17 by 14.
Yes, sir.
Not 4 by 4. What is it? We'll have to do
Minus
7,
11 by
3 is
4.
21.
Minus
4 by
11 by
Is
4.
it
7.
5 by
2 by
14 or
7.
something?
2 by 7.
Right, whatever it is. Yeah, it's 5 by 14, no?
By 14.
Sir, 2 by 7.
Sir, 2. Sir, it's 21
4
minus
by
17.
14.
4 by
It's 4
It
14.
by
is 4 by
14.
4 by
14.
14.
Oh, yeah, right. Okay. Yeah, whatever it is. That is not very important. Of course, you need to get your calculations correct. But now we are in RREF.
Yes,
Yes,
sir.
sir.
Yes.
Yes. So you did understand the general procedure, right? And you see that this is going to work every time.
Sir,
When
may
do
I
you have
ask
to swap?
something?
Just one moment. You have to swap rows when suppose you get a 0 row and that has to be at the bottom, correct? Or let's take an example to see where swap rows come in. Because here we have done multiplication of rows and adding one row to another. We have done it to get to REF and RREF. Is this procedure clear? What we have done for this particular example?
Yes.
Yes, sir.
But
Yes, sir.
the last
And
step,
this,
excuse me, sir. The
yeah.
last step, RREF, 2 by
Mhm.
7 and 17 by 14, right?
Mm.
So from REF to RREF, the entries are not necessary to be 0 and 1, right?
For REF, so what are the leading entry columns or the dependent variable columns? As soon as you get REF, you can determine that, correct? You only care about C1 and C2.
Okay, then by RREF,
For RREF, you just have to remove this guy because the columns containing the leading entries, they
okay,
have to have only 0 entries otherwhere
yeah,
in other places.
yeah, fine, thank you.
So you just subtract this and eliminate that. And you don't care about this. I mean, you care about it when you're solving the thing, but when you're verifying RREF, those constants are, it doesn't matter what. Now suppose I have, let's take a 3 by 3 example, 0, 1, 0, 1, 0, 0. This is a very easy example, but just let's begin. Now, is this in REF?
No, sir.
No.
No, sir.
Which rule is
No,
violated?
sir. Sir, 1 is at the right side, sir. First row. First row, first column, sir.
The second row is being violated.
Second row it is violating the right.
Yes. So what is the change that we can do to fix it?
Swap
So
the
you can
first and
swap the
second.
rows,
It should be R1 plus R2.
row 2 with row 1.
Yeah. If you do this, you will
Yes,
get
we
more.
can do this.
So even column also can be swapped here, right? C1 and C2.
No, no. The permitted things are only row operations.
Oh, okay.
Column operations are not allowed. I think this question was asked earlier as well.
Okay.
So we have to keep this thing in mind. Determinant should be vary, right?
Determinant should be?
Shouldn't be vary if you do any kind of row operations.
Swapping rows does change it, correct? Multiplying the row does change it. So determinant as it is not preserved. Even if it is in the case of square matrix. Here, this row operations, the concept of row reduction is valid for square matrices, non-square matrices, anything. So determinant is a thing which is specific to square matrices. And even in that case, determinant is not preserved by the operations. But there is an interesting point regarding determinant, which I will
Yes, sir.
highlight later.
Okay, sir. Okay. Yeah.
Yeah. For square matrices, this so primarily this row reduction is used for Gaussian elimination and finding the solutions of an equation. But for determinant as well, it has an application. So now, in general, you got an idea of how to do reduction. Reduction meaning using these 3 row operations to get to REF or RREF. Is that okay? Are you comfortable with that now?
Yes, sir.
The general, you can write a well-defined algorithm probably, but the general idea is that you look at the first row. If the first entry is to the left of or right of the second row entry, then you swap. If swaps are not, you determine whether swaps are required or not, and then once the swap is done, if required, then you look at the first non-zero entry. That has to be 1. If it is not 1, you scale it. And then everything below that has to be 0. So you do the required changes and then go to the row. You do row by row and you will end up with REF. And whenever you have REF, so what is REF? You have a bunch of leading ones and then you have these things are 0. Remember, the below is always 0. You don't need to worry about that. All you need to worry about is what happens at the top. So let's say 0, 0. As soon as you have REF, you have the numbers below the 1 to be 0 because of that. The next leading entry has to come to the right. That is a condition. That is rule number 2. So that will guarantee that all this will happen. It will be something of this form. Here I will have this to be 0. This also to be 0. And let's say this is 1. So this is some generic REF that I've written down. Now, if you want to convert this REF to RREF, whatever this thing is, if it is 0, then you're happy. If it is not, then you remove a appropriate scale of this row and you will get this to be 0, and these things might change. And then you look at things above here. You remove something from here, you remove something from here. This will not affect this part. So the structure will remain the same. I'm saying a lot of things just in vaguely words, not giving robust examples because I have to do Gaussian elimination as well. But I hope you are following my train of thought. Right. So
Yes, sir.
using this row, you can remove factors from here to make this 0. And these things might change. But once again, you use this row. So suppose you use this row to remove. So if you do something like R1 minus C times R4, R2 minus C times R3, sorry, R4 itself. This is another, let's say C4, C1, C2, C3. If you remove different multiples, you'll see that this part is unaffected because you have zeros to the right, correct? The only effect will happen over here. When you remove multiples of the 4th row from second, first, and third. First, second, and third. So you can make these things 0. And these guys I don't care about anyway because they are not part of my critical or the dependent variable rows. So this way you get an RREF from an REF. Once again, sorry for being vague about it, but yeah, you just solve an example, you'll get to know how to do it. Is that okay?
Yes, sir. Yes, sir. It's perfect. Actually, it's all clear for the RRAF
Yes,
and
sir. Got
RAF.
it, sir.
Okay. Now we'll go to Gaussian elimination.
Sir, just one question before that.
Yes.
To make the REF, we can do column operation as well as row operation. Is it okay?
No, you have to do only row operations. Well, if you want to get an REF form, you
Yeah.
can do column operations and get them too. But
Yeah.
the motivation or the reasoning behind doing row operations, I'll demonstrate using an example. But first, we'll finish this Gaussian elimination.
Okay, sir. Okay, sir.
Okay.
Yeah.
So this is changing the coefficient matrix, correct? So when you're changing the coefficient matrix, if you change the columns, it will be a problem. I'll tell you why later. So Gaussian elimination is, yeah, solving. The objective is solving AX equal to B. This is goal. This has been our goal for 2 weeks now. So finally, we will get the most general method to do that. So solving AX equal to B, in the last session, we have seen in case A is a square matrix, in case it is invertible, we have certain methods. But otherwise, we don't. And what we saw in the so far in this session is that if you have a general matrix, there is a way to convert it to a nice matrix. By a nice matrix, I mean REF or RREF. And once you have a nice matrix, then solving an equation is easier, right? So to solve AX equal to B, so the procedure is use row reduction, row operations, but I'll just call it row reduction. Use row reduction to obtain REF or RREF. RREF is slightly simpler to solve. You'll probably have to do a couple more steps from REF from A. This you know how to do, correct? You are given a system of equations. You form its coefficient matrix. It could be anything. You use your row operations to get REF form or REF or RREF. So let's say that's one thing. Do the same operations on B. Let's say REF form of A is A tilde. Okay. Do the same operations on B to obtain B tilde. Then you have that solutions of AX equal to B is the same as solutions to A tilde X is equal to B tilde. Once again, when I write it in words, it might be confusing. Let's take an example. I want to solve the system of equations. Let's say
Tilde
2x.
means,
Sorry?
tilde means?
I've changed as in you start with A, you convert it to the REF form. That's what I'm calling A tilde. Or let me call it A1, which is the REF form of A, or one of the REF forms of A. And
Okay.
B1 is the vector which is obtained by doing the same operations on B. What do I mean by doing the same operations on B? I'll tell you. Let's just
Sir, that augmented concept.
Yeah, you do the augmented matrix, and that is what I'm going to explain now. Let's just take some numbers. I don't even know if You will get nice solutions to this or whatever it is. So in this case, your A, I think in the lecture it is called R and this is called C. So maybe I will just keep it as keep it consistent with the lecture videos. So in this case, our initial coefficient matrix is 1 minus 2, 5, and B is 1 comma 2. So now we have to convert this to REF. First of all, that is what you have to do. But here is something that we will do simultaneously, since the rule says that whatever operations you do to obtain REF, you do the same on V. That is what this specifies. So you just put a vertical line over here just to say that the thing before the vertical line is the coefficient matrix and this is the constant matrix. You just write this matrix in this form. So it's like A vertical line B. This is called augmented matrix. Okay. Now start with this. You are going to do REF only for the part before the vertical. So what is the first operation that we will do?
Root
Let us
2
convert
minus root.
R1 by 2.
Uh,
R1 tends to R1 by 2. R1 equal to R1 by 2.
It's not tends to. R1 is changed to. It is, yeah, maybe not good notation. But yeah. Now,
We can do
we are,
subtraction also, sir. R1 is equals to R1 minus
just
R2.
a moment. What is after the vertical line?
Same
1
thing
by 2
divided
and
by
2.
2.
1 by 2 and
1.
1 by
Yes,
2 and
2
1.
also.
1
1
by
by
2
2
and 2.
equal to.
So whatever operation you do on whichever row, the corresponding changes you have to make in the corresponding entry for B as well. Okay. So if you do, you think of this as something a row containing 4 elements, but when your objective is to get the REF of A, the operations have to be in such a way that only that first part is an REF, but the operations are done throughout. Okay. And what is the second step?
Minus
R2 equal to R2 minus R1.
Equal to R2 minus
R2 minus R1.
Let's do this then. And so here R2 is changing. So R1 will remain the same. So I'll leave it as it is. Can you tell me what is R2, the new R2?
0
Minus 4.
minus 7 by 2.
3.
3.
Uh,
And 3 by 2.
3 by 2, yes.
Next.
R2 equal to R2 multiplied by minus 2 by 7.
Yeah, well, this is not going to be very pretty, the solution, but let's work it out. What is the second column?
0 1 minus 4 minus 6 by 7 and minus 3 by 7.
We can stop over here. We have got it to the REF form, correct? This
Sir,
part is in
RREF
REF
is
now.
not RREF is required, no?
No.
REF is enough. Let's do RREF. I'll tell you why REF is also enough. But for say RREF, what do I need now?
Should do this through
3
by
by
2
2
to be 0.
multiplied.
So 3 by 2
Yes,
will
sir.
be
R1 minus 3
R1
by
minus
2 R2.
R2.
What I'll get is this has to be this by definition. And what now? What are the other entries? Minus 3 by 2 R2 will be 18 by 9 by 7.
5 by 7.
Is it 2 minus 9 by 7? Yeah, which is 5 by 7. Yeah. So this will be 5 by 7. This is not changing. So this is not changing. So what is this entry?
It become 2 plus 6 by 7, right? 2 plus 9 by 7, right? Because there is a minus already.
There is a minus. There is, you're doing minus again.
23 by 7.
23 by 7.
Ah,
23
okay,
by
okay,
7,
okay.
sir.
2 minus 3 by 2 into minus 6 by 7. Huh?
Yeah.
Okay, 14 plus whatever. 23, is it?
Yes, yes.
Yes, sir. 23
Okay.
by 7.
And the other one is half
It will
plus
be 8 by 7.
9 by 14. 7 plus 9, 8. 8 by 7. Is that what you said?
Oh, yes, sir.
Okay. So now we are in RREF. So initially we had AX equal to B, and this is A, and this is B. Now we have an Rx is equal to C. This is R, this is C. Now what is the solution of Rx is equal to C? You'll have x1 plus 23 by 7 x3 is equal to 8 by 7. And x2 minus 6x3 by 7 is equal to minus 3 by 7. Is that fine?
Yes, sir.
X3 we can take C.
X3 you take it as C or T or whatever, and you will get this to be x1 is 8 minus 23t. I'm just taking it as t. You could take anything. Minus 3 plus 6 by 7, and x3 is equal to t. So the general solution is like this. 8 minus 23t by 7 minus 3 plus 60 by 7 and t. And as you vary t, you will get various solutions. You'll get infinitely many solutions in this case. Is the method clear?
Yes, sir.
Yes, sir.
So
Yes, sir.
solving systems of equations with RREF or REF is easy. So, but initially you might not have an REF coefficient matrix. You do the row operations to get your matrix to REF form, do the same operations on the constant vector. An easy way to do it would be to just put it next to the augmented matrix, to put it next to the coefficient matrix and do the row operations and do the corresponding operations on the last column as well. And then at the end, you get a new system of equations for which the coefficient matrix is actually RREF, and that you know how it is easy to solve. The result over here says that, where was it? Yeah, solutions of Ax equal to B are the same as the solutions of Rx is equal to C.
Sir, even this x1, x2 value for the linear equation can be resolved
Well, here just a moment. I've
using
written
the
x, y, z. That is x1, x2, x3. Sorry. Yeah.
So this x1, x2 can be found out using the Cramer's rule also. Even Gaussian also we can do. So what is the advantage it has over it, sir? Which one
So
we need to?
Cramer's rule is specifically for square matrices. In this case, it is not applicable.
Okay.
We can use determinant. Part
Determinant is
three.
also for only for square matrices, right?
Yes, sir. Right.
Yeah, and actually Gaussian elimination, so it has a very algorithmic approach, correct? So you can actually write a program to do this using Gaussian elimination, and it is known to be, I think it is known to be, I'm not very well versed in this, it is known to be faster way to do it than the other way, like computing inverses and all that. So this is computationally easier.
Sir, so this one, there is one more method, right? AX equal to B, where we do X equal to A inverse B. So that is also
Yes,
applicable
that
to square matrix only, right?
yes, that's also, yeah, inverse is only for square
Yes.
matrices. So there, if you look at the computational complexity for computing the inverse of a matrix and doing this,
Yeah,
I
yeah,
think
yeah.
it is known that Gaussian elimination is faster.
Right, correct.
That you have to check with someone who knows computer science more than me. So, but you will find standard references for that, I believe. Okay, so this is the procedure of Gaussian elimination, and this is, I've just given you one example. Listening to it is one thing. The only way to get expertise or familiarity is to solve questions by yourself. So you have to do that in the TA sessions and by yourself. Passive listening will only get you so far. Now I'll tell you why this method works or what is the motivation behind this. Like this, it is not magic, as in do why are only row operations allowed, why are not column operations allowed, and all that. The whole thing, the whole Gaussian elimination row operations reduced row echelon form is all an extension of what we generally do. So let's take, for example, this itself, this 2x, 3y, 4z, 1, 2x, I already forgot it, 4z, 1, x minus something, minus 2y, 5z. So if not for any data, if not for Gaussian elimination, how would you go about solving this? Let's call this guy equation 1, equation 2. How would you solve this if someone asked you just solve this equation for the set of equations for me?
Maybe by
X is
elimination.
equals to 2
First we
minus
draw
Coefficients of the variable.
augmented matrix. First we draw.
No. I'm not talking about the Gaussian elimination method.
So
If
we
you
directly
did not know this, how would you directly solve?
so directly
We can
X is
solve it
equals
by
to
substituting an
multiply 2 in equation 2, then
Okay.
1 by
just get
equation 1.
equation 1 and 2.
2 times equation 2 minus
Yes, sir.
equation 1 or
Equation 1.
something like that. I'll just
Yes.
do
or by substitution, sir.
But sir, we have
Substituting values of
two equations for three variables, right? So it is not possible.
Not possible.
Yeah.
Well, let's see if it's possible or not.
Okay.
So 2 into 2 minus 1 will give me what? Minus 5y? Not 5y. It will be minus, okay, let's just get it. X minus 10y plus 5z minus 2x plus 3y plus 4z is equal to 4 minus
10y.
So this is my new equation, correct?
Why this 10y,
minus
sir?
13y.
Minus 4y, sir, it will be.
Sir, it is 4y plus
Oh,
10z.
yeah, sorry.
4y plus 10z, yes.
Yeah, this is the new thing, right? So what is the
Yes,
new set
sir.
of equations? This thing is already there.
Minus
2x plus
7.
3y plus 4z is equal to 1. And here you will have minus 4y minus 3y, which is minus 7y. 10z minus 4z, which is 6z,
Plus 6z is equal to 3.
Equal to 3.
is equal to 3. Correct? So what you have done is taken one row. So what is the row? Row is the coefficients of the second equation, is row 2, correct? You have multiplied it by something and subtracted this thing. These are essentially row operations in disguise. For example, over here, the coefficient matrix 2, 3, 4, 1 minus 2, 5. We'll just write this also side by side without appealing to row operations. And let's see what happens in the new case. Here you have 2, 3, 4, 0, minus 7, 6, and 1, 3. what is the change that has happened over here? This is something like R2 has become 2R2 minus R1, correct?
Yes, sir.
Right? And scaling a, a row by something means just that you'll divide the equation by something, correct? So the next step, if I want to express y in terms of z, what will I do? I'll just do this 2x plus 3y plus 4z is equal to 1. And I'll say minus 1 by 7 times. So I just do y minus 6 by 7z is equal to minus 3 by 7.
Right.
And that corresponds to R2 becoming R2 minus R2 by 7.
Right.
And what are we doing? We are just doing the row operation and doing the corresponding operation on the augmented part also. So what row operations are just the same thing that you usually do to solve it, but reducing the noise by removing all these variables and just putting it in a matrix, doing it more nicely. That's all. And if you want it in some sort of, well, I could as well divide by 2 everywhere and make this also this, correct? R1 going to R1 by 2. If I want it in terms of some nice thing. And if I want to remove y from this equation, I can do that and express both y is equal to something in terms of z and x is equal to also something in terms of z. This is how I would go about doing the general equation. So your Gaussian elimination is the most natural way of solving the system itself, but just formalized nicely. And this is why column operations are not allowed, because then you cannot add things over from here to over here, correct? You cannot make 2x plus 3y as 2x plus, say, 7y. That you cannot do. That changes the equation. What
Right.
does not change the equation is the row operations, because row operations just mean that you are either scaling the equation or swapping the equations just means you are just writing the equation one before the other. And adding the constant multiples of one equation to another equation just means you are just rebalancing it in some way. And the equations themselves don't change. I mean, the equations themselves change, but the system of equations doesn't change. These equations change only up to, say, scalar multiples or constant multiples of one over another and all that. That is why the modified system over here will have the same solutions as the original system over here. Ax equal to b. Even though you are just saying that I'm doing row operations on an augmented matrix which has the coefficient matrix and the constant vector, what you're essentially doing is just rebalancing the equations as you normally would, just that you have removed all the variables and you're just playing with the numbers. So that's how you have to see Gaussian elimination, not that these are the rules and these are the row operations. So even if you say, for example, forget what the row operations are, what would you do to solve a normal system of equations? You would scale the equations, you would add one equation to the other or scales of one equation to the other, and swapping doesn't really have any meaning in the sense that swapping just means that you are writing one equation. You are writing the equations in any order that you want. So this is Gaussian elimination. And it's just a nice way of doing whatever you are already doing. Is that fine?
Yes.
Yes, sir.
Yes, sir.
Okay, I think that's about all the topics that we had to cover. And there is one more
Sir,
topic which maybe I'll tell the TA to cover about determinants. So how to compute determinants using row reduction.
Sir,
Yes.
what about homogeneous system of linear equation?
What about it? So the thing is, in a homogeneous system, so this did not appeal to whether the system is homogeneous or not homogeneous. So if we would be 0 0, it would do the same thing, correct? But under row operations, what you will see is that what are the row operations? Multiplying any row by a non-zero real number. So if you have a homogeneous system of equations, your last thing in the beginning will be 0 0. So if you multiply any row by a constant, this will also be multiplied by some constant, but it is 0 anyway, so it will remain 0. So if you add multiples of one row to another, you'll add multiples of 0 to this guy. 0 plus t times 0 will still remain 0. So this will remain 0. And if you swap rows, it will still be 0. So what happens in the case of homogeneous system of equations is that if you have a comma 0, that will be the augmented matrix. Then you'll have a reduced form comma 0 itself.
Yes, sir.
And then you can solve the reduced form comma 0 more easily.
Sir,
Yes.
Sir, they taught us about something trivial and non-trivial solutions.
Okay, so if you have a reduced system of 0, 0, 0, and if you have dependent variables, sorry, if you have independent variables, then you will. So the thing about homogeneous system of equations is, I think you have already seen it in the first week, that they will always have a solution. If you want to solve for ax equal to 0, x is equal to 0 is always a solution. So that's a trivial solution. So do there exist non-trivial solutions? So to see that, you will see that if you do the RREF of that or REF of that, and then you see that there are independent variables. So independent variables can take any value, correct? So you will have more than one solution, or in more than one meaning infinitely many solutions. So if there is a independent variable at the end of your REF for a homogeneous system, then it will have infinitely many solutions.
Okay, sir, got it.
Sir, professor said something different about homogeneous system of equations, sir. Sir, he said for coefficient matrix, if det is not equal to 0, then it has a solution 0, and if det is equal to 0, then it has infinitely many zeros. Sorry,
That is
solutions.
for the square system. That is for the if you have ax equal to 0 and A is a square matrix. This is the specific case which you are probably talking about. Now, if determinant of A is non-zero, then what is the unique solution that we have seen is A inverse B, correct? But A inverse times, this is the 0 vector. So this will be 0. So x is equal to 0 is the unique solution for that. But if determinant of A is non-zero. But if determinant of A is equal to 0, then you will have a independent variable. So that comes because of, let's say, a 3 cross 3 matrix. What would be are you convinced that the RREF of that will be an upper triangular matrix?
Sir, could you give an example, sir, for both? That would be good.
Yeah. Okay. Let's take 1, 2, 3, 4, 5, 6, 7, 8, 9 itself. So x plus 2y plus 3z is equal to 0. We know that this is determinant 0. Last time we saw this, correct? I don't know if you were there last time, but yeah. So this, your coefficient matrix is 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if I do for a homogeneous system, you don't need to write this 0, 0, 0 part. I'm just going to write it, but you don't need to write it. You will quickly see why. You probably already see why. So the
Here
first thing
determinant is
is,
0.
sorry?
Here determinant is 0.
Yeah, determinant is 0. But
Yes,
let's
sir.
do the RE. So first of all, let's observe that determinant is actually 0. Determinant of A is 0. Now let's continue. Whether we'll see, we'll get infinitely many solution or a unique solution. So yeah, what is the operation that we have to do? The first row can be kept as it is for now. And then I have to do this minus, say, 4 times R1, correct?
2 times, yes. Good.
8 minus 3, 12 minus 6. This will remain 0. So that's why I'm saying that this is irrelevant. I'll do this also. R3 goes to R3 minus 7 R3. because I want a 0 here also, correct? So I'll do that simultaneously.
7 R1.
6.
Right. 14,
Minus
86.
6. Yes, sir.
And 21,
7,
12.
12, yes, right.
Yeah. Now I already see something. So even before I normalize, let us normalize it first. Let's do R2 becomes minus R2 by 3. We'll have a 1, 2, 3, no change. 1, 2, 0, 0, 0, 0 minus 6, minus 12. Then if I do R3 becomes
Minus
R3
R3
plus
by
6R2.
yes, right.
We have 1, 2, 0, 0, 0. So, okay, let me quickly tell that determinant thing as well, as we are already here. So, if you are doing a square, if you have a square matrix and you do the procedure to RREF, so what are the things that you're doing? You're either swapping two rows or you're adding constant multiple of one row to another, which does not change the determinant. If you remember the property of determinants, swapping the rows changes the determinant by a negative sign. And what is the other row operation, which are multiplying
Adding
the
multiples of one row to the another.
adding multiples of one row to the another does not change the determinant. Swapping the rows changes the determinant by only a negative sign. And the
Yes,
other
yes,
thing is multiplying by a non-zero scalar.
yes.
Correct? So if I have a matrix over here A, and if I have a matrix over here R, the resultant matrix after REF, if determinant of A is non-zero, then determinant of R is also non-zero.
But will not same.
But will not be same because you are multiplying by a scalar at some points, correct?
Yes,
If you keep track of what the changes that you are making, you can write it in terms of that constant, some C times or minus C times. There will be
and the
some
determinant.
yeah. You can backtrack and see what the changes you have made are, and then you can actually compute the determinant as well. But the other way is also true. If determinant of A is 0, then the determinant of R will also be 0. Why? Because if you multiply by a row by t, your determinant gets multiplied by t. So that is 0. 0 remains 0. If you swap rows, you'll get a minus sign. Minus of 0 is 0. And if you add constant multiples of one row to another, the determinant doesn't change anyway. So the determinant is unchanged. So if this is both ways, so determinant of A is 0 if and only if determinant of R is 0. Correct? So one way to compute determinant is to compute the REF of that, and the REF of the determinant will be easy to compute because REF will always be an upper triangular matrix, correct?
Hmm?
Do you guys agree that REF of a square matrix is an upper triangular matrix?
Oh, yes.
Can
Yes.
you
Yes.
mute your mic, please? Uh, all right. So yeah. In this case, you see that determinant of A as it is might have been difficult to compute. If you do the REF, what you have is 110 on the diagonals, and that is expected. And determinant of this R is easy to compute because it's just 1 into 1 into 0 because it's an upper triangular matrix. It's just product of the diagonal elements. So that is 0. That's one way to compute the determinant. Now we kind of went away from our original objective, that which is to solve this system of equations. Since it is going to be an upper triangular matrix, the modified system, and it will have 1, 1, 1, and in the best case scenario, or these things will be 0. This will be either 1 or 0. This will be either 1 or 0. This will be 1 only most of the time, at least, or it could be 0 everywhere. But the point is, it will always have an independent variable. If the determinant of A is equal to 0, this has to have one of these as zeros. Otherwise, the determinant of this will be non-zero. If it is 1, 1, 1, the determinant of this will be 1, but the initial assumption is that determinant of this is 0. So this cannot happen. It will
Yes, sir.
happen something like this, or possibly even something like this. But in any case, the upshot is that there will be at least one independent variable. So as soon as you have an independent variable, that is free to take any value. So you'll have infinitely many solutions. So the conclusion is it was kind of rushed, and I could not do it better than this. I'll probably tell the TA to cover it in this TA session. Determinant of A is equal to 0 implies infinite solutions. Implies, let's say, existence of independent variable. This implies infinitely many solutions. In this particular case, you see that the dependent variables are corresponding to column x1 and x2, and x3 is an independent variable. So,
Sir, if determinant A is not equal to 0, then unique solution, or
then you will get unique solution, because if determinant of A
Sir,
is not equal to 0,
for
just
square
one
matrix, you
moment.
said for 0, right?
Could you repeat the question?
Like for the square matrix, if we are solving homogeneous system of equations, then if that is not equal to 0, then we'll get 0 as the solution. That was my question, sir.
Yes. So the thing is, if you start out with a determinant not equal to 0 matrix and then do its RREF, it will be of the form, it has to be of the form this. Because determinant, if it is non-zero initially, the determinant of your RREF matrix also has to be non-zero. And this is the only way that it is non-zero. Right?
Yes, sir.
REF I'm talking about. RREF means it will always be this itself.
Yes, sir.
Because you should have at least one right shift, and you cannot have more than one right shift, because then it will be problematic. Correct? So it should be exactly one right shift, and it has to be this. If you start out with a determinant non-zero matrix and do its REF, REF will just give an upper triangular matrix. RREF will give you the identity matrix. If you are okay with this fact, then you see that it's a unique solution. No, you'll not have any independent variables. You'll get x3 is equal to some b3, then x2 is equal to b2 plus something times x3, and x1 is equal to, and x3 will come in terms of b3, and x1 will come in terms of b1 plus something times b2 plus something times b3. Do you see this?
Yes, sir. My doubt was like in the lecture it was saying 0 as the solution. Like we're having three different values, right? Unique solution we are getting, but
Okay, yeah, we are in homogeneous solution, right? Homogeneous case, 0 is always the solution. And if it is a unique, if there is only one solution, then that has to be the only solution.
Sir, so from Gaussian elimination, we can
Just one moment.
state.
Well, let's finish his doubt. Let's get done with that. Are you clear, or are you more confused now?
yes, sir,
Okay.
I'm confused. Like for non-zero, for that equal to non-zero, then how is for a square matrix, how is it 0? Could you explain me that by an example,
Yeah.
if possible?
Okay, yeah, we'll take an example, but let me just tell you quickly, following up on what we were saying, since you had said that you're okay with the fact that uh, the REF of that will be upper triangular. So after I do REF, A0 will become something like this. Is that okay?
Yes, sir.
So how do you solve this now? You will get x3 is equal to 0. Let's put this as ABC. Okay.
Yes, sir.
X3 is equal to 0. X2
Yes, sir.
plus CX3 is equal to 0. and x1 plus ax2 plus bx3 is equal to 0. So x3 is equal to 0, but x3 is equal to 0 here will give me x2 is equal to 0.
Okay. Yes,
And
yes, I got it, sir. Yeah, yeah.
this is x1 is
Clear.
equal to 0. You can work out with a specific example if you want, but I think now you got it, right?
Yes, yeah, I was roaming around it only. Yeah, I got it. Yeah,
Yeah. So the
yeah.
main
Thank
point
you.
is that if you start out with the determinant 0 matrix, the REF will be an upper triangular matrix, and the RREF will be the identity matrix.
Yes, sir. Clear, sir.
Okay. Yeah.
Thank you.
Other doubts? Yeah, you don't need to raise your hand. You can speak
Yeah,
out. As
so
long as it's
I
one
just
at a
had a
time.
doubt about this the infinite solution thing.
Mhm.
In one of the questions, there is also the case of no solution where they give B has two parallel lines, sort of.
Right. So here the B is 0. So we were discussing over
Oh,
here
only zero.
specifically homogeneous system. So in
Okay.
homogeneous system, you always have a solution.
Yes.
So there you have only unique solution or infinitely many solutions. So that is in correspondence with the determinant being non-zero or 0.
Okay. Yeah.
All right. Other doubts?
Yes, sir, I had one doubt.
Yes.
So from Gaussian elimination, we can state that any system of every system of linear equation must have at least one independent variable, right?
No, why?
Uh, like
So let's
we
take,
have
for
seen.
example, okay. Let's take an example. This is sort of, I'll fabricate a very easy thing. Suppose you get at the end of your uh, REF or RREF, you get this as your coefficient matrix. It is an overdetermined, as in let's not use that word. It is a system of equations where number of variables is less than the number of equations. Then here do we have independent variables?
No.
No, right? We have only
No.
two variables. Both of these
Yeah.
are dependent.
Both of yeah, both of them are dependent.
Yeah, and this might not even have a solution because the augmented matrix might look like something like 1, 2, 3. Say let's suppose that at the end of your RREF procedure you got something like this. But what does this mean? 0x1 plus 0x2
Can't
is
be
equal
equal
to
to
3. So 0 is equal to 3, which is not possible. So there's no solution.
Okay, okay,
So,
got it,
so
sir.
at the end of your RREF, if you have 0 rows and the corresponding constant coefficient has not become 0 in the process of the REF, then you can conclude that the system does not have any solution.
Okay, sir, understood.
Yeah. Okay, then. Any other doubts?
So,
Yeah.
sir, just wanted to clarify something. Sir, I'm trying to make a generalized statement. Let's say we are having a homogeneous equation and we find out that the determinant of that matrix
Square
is
system,
0.
number of equations, number of variables are the same.
Maybe, I mean, it depends. I mean, it's not, let's
Then
say,
you can't talk about determinant, right?
let's say it's a square matrix.
Okay. Ax equal to 0.
Then we can say that we can either have a unique solution or infinite solution.
Yes.
And the same for non-homogeneous equations.
No, for
Let's say if
non-homogeneous.
it's
Okay, go ahead.
let's say we have a square matrix, then either we'll have an infinite solution or we'll have no solutions.
No, they can be unique also. Determinant of A equal to not equal to 0 gives you a unique solution. There, all three cases can happen. No solution, unique solution, and infinitely many solutions. So I think
For non-homogeneous, how will we get a unique solution for sir, when the determinant is 0, sir?
determinant is not 0. Only then.
I'm saying determinant is 0.
Oh, is 0. Okay. Yeah. If it is 0, then yeah, you have only these
Then
two
either we'll have infinitely many solution or we'll
Yes.
have no
Yes.
solution.
Yes.
Okay, sir. Thank you, sir.
Yeah. Okay. If there are no more doubts, then let's wrap up.
Thank you, sir. Good night.
Good night, sir. Thank you.
There were some other questions that I said I'll take up at the end. Was there anything in particular? I don't remember